In the development of space, the most prevalent and safest propulsion technology is the liquid fuel engine. The future workforce in this field is currently in school, particularly in college, which has led multiple groups to launch liquid fuel rocket competitions to give students a jumpstart on their experience, the largest of which is the Base 11 Space Challenge. But Texas A&M has not had a program developing liquid fuel rockets. So this team, Texas A&M University Rocket Engine Design Team, which we shortened to TAMU-RED, began. A new team means little money to work with, so we have been working to figure out how to go from this to this. We decided that by the end of the year, RED would develop its first liquid fuel rocket engine. From this, RED would develop the highest performing collegiate rocket engine to use in the Base 11 Space Challenge within the next 2 years. In 5 years, in order to meet the founding members' vision, TAMU-RED will develop the first pump-fed rocket engine on the collegiate level. Our first step is Genesis version 0.0, which has allowed TAMU-RED to begin the development of liquid rocket capability for Texas A&M. It utilizes liquid methane, the fuel of the future, to maximize its performance. Genesis also uses film cooling to keep the engine from melting like ice cream under extreme heat, which saves weight and complexity with little loss in efficiency. The first engine will use a showerhead injector within the engine that allows for a simple injector design that can maintain safe and reliable operation. Genesis balances cost, power to weight, and efficiency in order to get the most out of every dollar put into its creation. The simple design allows for a quick development cycle, which will allow TAMU-RED to take a hardware-based approach to rocket engine development. Most importantly, Genesis can be scaled up from an experimental demonstrator engine to one that can be used to propel vehicles to the edge of space.
The thrust chamber is the crucial component that generates 500 pounds of thrust to power the Genesis engine. This version was designed to be simple and durable without regard to weight. This allows design principles to be tested and verified before margins are reduced for future engines designed for flight. The geometry is the most important design aspect of the thrust chamber. The combustion chamber must have enough volume for the propellants to mix, the converging section must choke the flow until it reaches Mach 1 at the throat, and the diverging section must expand the flow until it reaches ambient air pressure at the exit. The precise shape of the nozzle was calculated using isentropic relations and other established formulae, using target parameters such as thrust, efficiency, and chamber pressure as inputs. This geometry was then validated through simulations in ANSYS Fluent, which demonstrated that the flow behaves as intended, reaching Mach 1 at the throat, and then continuing to accelerate as it exits the nozzle. The thrust chamber also needs to withstand the frightening temperatures of combustion for prolonged periods of time, while maintaining structural integrity with 225 psi of internal pressure. For early testing, the engine will only fire for a few seconds at a time and is not intended to fly. Cost effectiveness, durability, simplicity, and ease of machining were therefore optimized at a minor expense of weight, for the most effective path to our team's first engine. 316 stainless steel was selected to meet these needs. As mentioned earlier, our engine is kept cool by injecting excess methane along the inner walls of the chamber, a technique known as film cooling. This ANSYS Fluent simulation demonstrates how film cooling brings the temperature at the walls from nearly 3000 Kelvin to about 800 to 1000 Kelvin, at which temperature 316 has a yield strength of 120 to 140 megapascals. With a wall thickness of 1/8 of an inch, the pressures inside the chamber generate a working stress of less than 30 megapascals as seen in the SolidWorks simulation. Additionally, in the worst case scenario that the full engine thrust is directed along the chamber walls, the steel only needs to withstand about 8 megapascals of stress, well within its strength at temperature. The stock material was acquired for less than $300, and future work includes fabricating the first prototype, characterizing thermal stresses in the material, and finally testing the nozzle with the engine assembly at the end of the test campaign.
The function of the propellant feed system is to provide fuel and oxidizer to the engine for the combustion and cooling process. Because of the Genesis engine is pressure fed and film cooled, the propellant feed must supply enough fuel at the design pressure to facilitate desired thrust and maintain safe operating temperatures in the combustion chamber. The propellant feed needs to be able to operate and service safely and be scaled up for future engines with more demanding operating parameters. The propellant feed can be broken into separate subsystems that each work together. These subsystems are the storage tanks, feed lines, and valves, and finally the pressurization system. These subsystems were designed with the budget as the main concern and weight as the second. The fuel tanks store the cryogenic methane used as the fuel and the cryogenic oxygen used as the oxidizer. The tanks need to be capable of a maximum internal pressure of 700 psi, while at cryogenic temperatures between -150 to -273 degrees Celsius. The budget for the fuel tanks was $800. With plans for future engines to compete in the Base 11 Challenge, the tanks were required to fit certain geometric constraints. As well as being reusable in the future, the tanks could be no larger than 6 inches in diameter. To connect each subsystem and have control of the propellant's flow, a system of feed lines and valves were designed. The subsystem had to meet all the performance requirements of the Genesis engine, interface with the avionics, and facilitate safe fueling and dumping of the methalox combination. The fuel lines must be able to receive pressure from the pressurization system at 250 psi and conduct cryogenic fuel from the fuel tank to the injector plate at a rate of 21.3 gallons per minute. For safety, cryogenic pressure relief valves were placed on top of each fuel tank with vent lines running 25 feet in opposite directions. This is to prevent fuel from mixing in the event of a pressure valve venting. Cryogenic hoses were purchased for the fuel lines and stainless steel quick connects for connections. An assortment of solenoid valves, electronically actuated dump valves, and check valves were also used in different parts of the assembly. The pressurization system uses the inert gas helium to supply pressures as high as 300 psi continuously throughout the burn. The system must be controlled remotely as well as by an onboard computer. And again, the system must be built cost effectively. A pre-built 4,500 psi composite tank was used in conjunction with the 800 psi regulator to store and release the helium. The tank and the regulator come already tested at their max pressures. Tests will also be done on the system before placed in line with the tanks. This system has been purchased and assembled. Currently, the system is being finalized with the avionics team to configure controls for the valves.
The avionics and control system ensures the safe, automated, and remote operation of the engine during testing and provides telemetry for measuring engine performance. Avionics consists of a number of subsystems, including an electronic control module, or ECM, power supply, valve actuators and solenoids, electric engine igniters, and telemetry modules. The ECM controls engine startup and shutdown, monitors engine telemetry, automatically aborts testing in the event of a system failure, and allows remote access to engine systems. Reliability, simplicity of installation, and adaptability to future applications are all needed. To meet these requirements, an Arduino-based PCB was selected. The Arduino platform offers flexibility and open-source software to reduce production time and allow transitioning between multiple engine configurations. Rigorous testing of the ECM before operational use will ensure the unit's quality and find programming errors. Power supply irregularities could quickly lead to loss of control of critical safety systems, and therefore reliability of the power system is vital. Batteries offer the simplest and most portable option for remote engine operation. Commercially available RC aircraft LiPo batteries were selected from a reputable manufacturer. These batteries are quite reliable and safe when handled properly and in accordance with safety documentation. Valve actuators and solenoids are used to control the flow and dumping of propellants and pressurization gases. CNC table stepper motors were selected to actuate valves, allowing precise high torque control. Solenoid actuated valves were selected for lines requiring rapid flow control. Solenoids were used where possible to reduce overall valve assembly costs. Preliminary testing has been completed, and in future tests the valves will be tested under pressure to simulate operating conditions. Starting the engine requires igniting the ejected propellants reliably. A consistent high-energy flame is required from the igniter to ensure that the main burn starts in a controlled manner. To accomplish this, an electrically controlled pyrogen chemical igniter was selected. These igniters provide high reliability and high total thermal energy. The igniter will be activated using an electrical relay, allowing remote control of the engine start. Pressure, temperature, and thrust data must be collected during engine tests in order to measure engine performance parameters. These parameters will help to improve future design iterations. To collect this data, multiple load cells, pressure transducers, high-temperature thermocouples, and high-speed and thermal cameras will be employed. Specific components were selected based on price, availability, and expected operating conditions. Component ratings were determined to only reasonably exceed expected requirements in order to reduce cost. Data from these modules will be relayed through the ECM to the same remote computer being used to control the engine test. Due to the non-critical nature of the telemetry system, only basic operational testing is required to ensure functionality.